how do we spell numbers? The first is 0. I think I have steals, but I don't think you will see it. I can make some marks like this. Do you see the mark?
Yeah.
Okay. Okay, so it works. So the first and the simplest one, 0, or we can say not. It was a surprise for me. I never heard about not. Or simply O. O as 0. Then 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Every single one is a digit. Then a set of natural numbers is denoted by x belongs to n. The set of integer number is denoted by z. For sure, you know all of these objects, but we have to pronounce them correctly in English. Then real numbers and their set of complex numbers with a as a real part and b as imaginary part of a complex number. And I is the complex, well, complex one. Next, decimal fractions, like 1.5. The delimiter between the natural number and the fraction is called point. So 1.5. Next one, it is an example of spelling. For example, 45.1 and so on. Next, when there are a lot of digits after point, we do not call 2.45. It's a wrong spelling. We have to say 2.45. So every single digit is pronounced individually. Next one, 0.06 or 0.06 or 0.06 or 0.06, doesn't matter. In English, we can say only point and some numbers after the point. So if the first digit is 0, we can avoid spelling it. So just 0.06. Next, if the number can be divided by 2, it is called even. If not, it is called odd. And the set of well-known prime numbers, I think we have to add 2 to this set. These are primes. Next, some actions. Actions, the equalities. Equalities, x equals to 0 or x is equal to 0 and so on. Next action is addition. The action is addition, and we say 2 plus 3 is 5, or 2 plus 3 total 5. We substitute the equality with is total. Next one is subtraction. With 5 minus 2, 3. Then multiplication. Multiplication, we say 2 multiplied by 2 is 4, or 2 times 2 equals 4, or a product of 2 and 2 is a 4. Next is the division. Division. Next one is negative numbers. We say minus x or negative x. Next action is when A is approximately equal to B, or A is greater than B, or A is less than B. These are these actions. Next one is absolute value or magnitude of X, or mean value. Some brackets, round brackets, square brackets, and braces. Next, fractions. A divided by B is a common fraction with A as a numerator and B as a denominator. I will send you this presentation, so so you will have everything you need to prepare for exams. Next one, mixed natural. That consists of an integer number and a common fraction. And some of common fraction have the names themselves, like a half, third, a quarter, and so on. 1 1/4, 1 1/2, 1 3/4. So I think it's quite simple. Next, some indexes, powers, and roots. A sub m, or if there is only one index, doesn't matter lower index or upper index, we can say simply am or amth. A0, A0. The upper index is pronounced as super, so B super n. We say the first is in this spelling, the first is B, and they will say super, and then we call the power B super n. When there is some mixed index, we call it C sub mn super gk. C sub mn super gk. Some powers, we say x squared or x raised to the second power, or the square of x, or the second power of x. Y cubed, y to the third power, and so on. If we raise some number or variable to negative power, we say z to the negative 10th, for example, like here, or z to the minus 10th. The power can be mixed nature itself, for example, like this, t to 3/2. Some roots, the square root, the cube root, the root of the power n plus k of 7, like this. The fifth root of b to the 4th, and so on. Or the most general case, a raised to the power of b, or a to the power of b. And some examples with equalities, like this. So the square root of 16 is 4. Another interesting thing, when we have some braces, and we need to make some operations inside the braces, we can say 2 plus 3 quantity. Quantity means this action is in the braces. 2 plus 3 quantity times 4 is 20, or times 4 equals to 20. Or like this, 3 plus 5 quantity squared is 64. So if we want to stress that this sum is raised to the second power, we say quantity before the power. The next one, some operations of containment. Containment means that one set belongs to another set, like this. I have no ideas why I started this slide with factorial, because it is not operation of containment. No ideas why. Well, so some intervals, open interval from A to B, closed interval from A to B, and open from the left interval from A to B, and closed from the right interval from A to B. And the same if it is open from the right and closed from the left. Then if A is a vector, we call norm as a norm. And then some sets. Well, do you see a mistake here?
Sorry, again?
0 is not natural number.
Yes, sure. 0 is not natural. So don't make this mistake. 0, it's not natural. So it is the set of non-negative integers, but not naturals. Okay, next one. X belongs to A. X is an element of A, or A contains X. So if X does not belong to A, we denote it as this sign. If A and B are some sets, then we have some another operations of containment, like A is a subset of B, or B is a subset of A, or A is not a subset of B, and so on. This notation is used for boundary of A. What does it mean, a boundary? Can you give a definition? What is the boundary of a set?
Edge points.
Yes, I think it is the simplest and the best definition, because the definition of the boundary of a set is quite difficult if a set contains of infinite number of elements. There can be some problems with the definition of the boundary, like it is a point, so that exists some sequence of points that belong to the set of A in some region, in some neighborhood of the point. The definition can be difficult. Usually, in these lections, we do not focus on mathematics itself. We mostly interested in the results. For example, we consider some biological models. We examine its mathematical features, and we do not focus on mathematics itself. We focus on the biological results. For example, if there is some community of species, we are interested what will happen. Do this community vanish, or all of the species will die in this situation, or, for example, not? So I'll try to avoid some complicated mathematics. We'll try to focus on the biological meaning. Next, some quantifiers. The quantifier for any or for all. Quantifier existence. So it's just the letters upside down. So A upside down is the quantifier any, and the reversed letter for existence is the quantifier exist. The quantifier the only, and they're simple such that. For example, one of axioms is spelled for any real R, there exists a positive natural n such that n is greater than R. As far as I remember, it's a Euclid axiom, but maybe I'm mistaken. I don't remember.
Archimedes already.
Oh,
Archimedes.
thank you. Thank you. Maybe Archimedes. It was too many years ago. Next one. For any natural n, there exists the only real z such that z is equal to negative n. It's another axiom. Axiom of existence of negative numbers. Functions. Y equals f of x, or y is a function of x. Here, y is the result of the function and x is argument. For inverse functions, we have following notification. And we can spell it as x equals f inverse of y. Oh, I think y equals f inverse of x. Because here x is an argument. Next one is a simple equation. The most interesting, we spell this part left-hand side and this part of equation right-hand side. Left and right-hand side of the equation. Next one, some sequences. Sequence x and the spelling sequence x n goes sequence x n as n goes from 1 to infinity, like this. If we calculate the sum of the sequence, we get a series. If this series converge, we can say that sum of xn as n goes from 1 to infinity is equal to s. Or like this, a sequence xn converges to a, or simply xn converges to a. Some more complicated situations like xn converges to a as n tends to infinity or goes to infinity, or as n approaches infinity. If some sequence do not converge, we can say that xn diverges, or xn diverges to infinity, or goes to infinity, or approach infinity, and so on. Can you give me an example of sequence that diverges to infinity?
Fibonacci sequence.
Once more, please.
Fibonacci sequence.
Whoa, Fibonacci sequence. Yes, okay, Fibonacci sequence really goes to infinity. That's right. I expected for something like n goes to infinity, as n goes to infinity, or any power of n. Yes, Fibonacci is okay. Next one, if a series converges to a, if a is a real number, then we say that series converges to a, or a contrary, if it doesn't converge, we say that it diverges, or sometimes the sum doesn't exist. Give me, please, an example of a series that doesn't exist, when sum of the series doesn't exist.
Xn is equals sinus n.
Okay, got it. I think that's right. This series will not converge, but usually the simplest one is -1 to nth power. So the sum of this series change from 0 to -1 and come back to 0. I think there can be some difficulties to prove that this series sin n doesn't exist. That's the real question, how to prove it, that it doesn't exist. I think we have to use the definition of the limit, and we can see that the elements of this sum are not decreasing. So so it doesn't exist. Okay. Next one, some limits. The first one, limit of xn as n tends to infinity is equal to a, or xn converges to a as n tends to infinity. If our variable approach to some point from left or from the right side, we use this notation and we use this spelling. And some other examples very similar to series. Approach, converse, the same words. Next one, derivatives. Derivatives, for the first derivative, we say derivative of f prime. The second derivative, double prime. Next one will be triple prime or nth derivative. We use this notation with the brackets. The same is a spelling derivative of f of the order n. When we want to stress that we calculate the derivative with respect to the variable x, we use this notation and we say we spell it derivative of f with respect to x. Some more useful notations as increment of x or differential of x. Then if we need to write the definition of derivative, we can spell it df by dx, or derivative of f with respect to x, and so on with the second derivative or partial derivative. Partial derivative df by dy, or partial derivative of f with respect to y. And the same with the second partial derivatives. Second partial derivative of f with respect to x and y. Some integrals, integral, double integral, triple integral, indefinite integral of f of x dx, or we can say general antiderivative. General antiderivative, so if we calculate the derivative of general antiderivative, we can get our x. Integral with some boundaries. When the boundaries are not infinitive, we use proper integral. Sometimes the integral can be improper when one or two limits are infinitive. Sometimes we integrate over some set, so integral of omega over set gamma. Some another notations, minimum, maximum. We say x runs over a if we consider only x that belongs to some set. We say that x runs over the set. And so on. If here alpha runs over a. And sometimes we use product. Product also can be used. Next one, differential equations. We'll use a lot of differential equations because almost everything that that can be examined in the real nature can be described by ordinary differential equations. Everything that changed can be considered as a smooth function, and then we can calculate the derivative and so on. So we'll use them a lot. So the first derivative, if their variable is time, we usually use x dot to stress that x is the function of the time, and we calculate derivative with respect with time. Our ordinary differential equation, x dot is f of t and x. X of t is the solution, or the same, it is integral curve. T we call as independent variable. Then, if there exists a point x1, a constant x1, such that the right-hand side of the equation satisfy f of t and x1 is equal to 0, then we say that x1 is an equilibrium or a fixed point or a steady state of our differential equation. If x1 is 0, then we say that in the equation there is a trivial solution. If the right-hand side do not depend on the time, we say this sort of equation autonomous. Autonomous, then some sorts of our differential equation, a linear homogeneous equation and linear non-homogeneous equation. For equation x dot is x, the solution, the general solution, is called a complementary function. So it is the set of functions with some variable c. This set is called complementary function. Some solution of differential equation is called a particular integral. So one of the solutions is a particular integral, and any of the solution is called a particular integral. The sum of particular integral and complementary function for linear differential equations is a general solution. General solution. So it contains of a complementary function and particular integral for linear case. Next one, we are interested. Usually, we are interested in the solution of Cauchy initial value problem. We usually know the actual situation, and we are interested what will happen with our, for example, biological community in the nearest future. So we usually have some initial value. Next one, a bit more complicated. If for differential equation, the right-hand side of our equation can be, so the equation is y dot, no, y prime is f of x n, like this. If we rewrite it in differential form, so dy divided by dx is our f of xy. Then we multiply by dx, and then we get something like this. So if for this sum exists a function f such that df is pdx plus q dy, then we call this function f as exact differential. Sometimes we use it for solving. And when we multiply the equation by some function to make sure that the exact differential exists, we call this function integration factor. Sometimes we use it. And some more equations. The second order equation, the equation with separated variables, the simplest one. It can be easily solved. The homogeneous equation, if the right-hand side satisfy these conditions. Next one, when we solve linear equations, we usually calculate eigenvalues and eigenvectors. Here, for linear equation, lambda is an eigenvalue and x is an eigenvector. So that's all about spelling. And we can start with our mathematical models. A few words about models. We can't say that we can consider differential equation for any type of the models. In the real life, there are a lot of situations when we cannot use differential equations. So the first part of our lections will be connected with the models that can be described with differential equations. So we must introduce some propositions to ensure that our biological community can be described with differential equation. We usually are interested in the amount of biomass, and we consider what is happening with this amount. So we are not interested in every individual, but all the population in general. So let us denote the population size as n of t. T is, as usual, is our time. So we need some propositions. to consider the smooth function n of t. What are these propositions? First one, the individuals in the biological community must be evenly distributed in space. The first one. In another case, we have to divide our space in some regions when the biological community is homogeneous in these regions, and then we can try to describe every region itself. The second one, the population is homogeneous by age and sex. So all of the species are maybe not the same, but they are similar. They can be described in these smooth functions. Next one, very important. The reproduction process is continuous. Well, the simplest case when the reproduction process is not continuous, the insects. We know that the insects in autumn, they lay eggs, and these eggs are waiting for the summer, for the spring. In the spring, all the eggs hatch out simultaneously. And if we drive the, if we write the plot, here n of t, and here is our time. So there is some insect population. It is the autumn. At this moment, they lay eggs, and they all are dying. In winter, there are no insects, no bees, no flies. They are sleeping or they are dying. Then, this is the winter. Then in spring, the eggs hatch out, and we have no new population number. So the plot will be like this. For sure, it is really absolutely impossible to use smooth functions because of this the not smooth shape. So for insect population, we use another type models when we fix only springs, for example, and we consider the spring number 1, the spring number 2, the spring number 4, and so on. So we have to use difference models. When this situation, when the process of reproduction is continuous, it is mostly mammals. Mammals, do you know who are mammals?
I mean, yes. Do we need to translate for us?
Can you explain?
Mammals are animals that have hair and feed milk to their children, basically.
Yeah. Yes, thank you. Mammals feed the children with milk. Yes, it's the exact definition. So there are some mammals who reproduce like insects in the end of summer, for example, or they reproduce in spring. But there is a lot of mammals that reproduce every time they can. For example, our human population. No problem. The reproduction process is absolutely continuous. And the final proposition, the total number of individuals must be quite large. So our n of t is usually much greater than 1. And if one of the species dies, it doesn't affect all the biomass of the population. Next one, the population size means not the number of species itself, but usually we say that it is the biomass. For example, biomass of people, or biomass of some rabbits or elephants. We can compare them. It doesn't mean that the size of one species. So if all these propositions are satisfied, there is a big number, the reproduction process is continuous, and so on, then we can use the continuous functions. And we can say that function n of t can be continuously differentiable for any positive time. We usually consider only positive time because we consider the zero situation, zero time, it is the actual situation, and we are looking to the future. So first of all, the biological meaning of the population size is that it is non-negative. Our population is always non-negative. If the population become equal to 0, that means that the population vanish and it can't become negative. And usually we have some initial value at our initial moment. I think we should use 0 here instead of t0. So let us start with the very basic models. The first model was introduced by Thomas Malthus. It was an Austrian demograph. He lived 200 years ago, more than 200 years ago. So the first model was really very simple. The first and basic one. So what is the idea of Malthus? Let us consider some specific birth rate. So it is the number of individuals who was born per 1 unit. So we divide the number of individuals that born, we divide it by the total number. And the same be as the specific mortality. It is the number of deaths from any situations, from predators, from disease, from old age, and so on. So all the birth and all the who dies. And we consider the simplest case when the difference between A and B is constant. So the first equation is called Malthus equation. It was introduced in 1798, and it is linear. If the Cauchy initial value problem is n of 0 is n0, we can easily solve the equation. We can divide variables and integrate and so on. I think solving of this equation is not a problem for you, for grade students. So we can simply write the general solution as an exponent function. T0 is 0, so the general solution is n0 exponent of at. So let's examine this model. What's happening when we have two two constants here, n0, that is always positive, because we consider the existing community, so n0 must be positive. And we have the constant a that can be either positive or negative. So let us calculate the limit of n of t with time approaching positive infinity. So what's happening with our community? We can easily see that if a is positive, then the population size will endlessly increase. And if a is negative, then the population decrease to 0. So the population will vanish. So the first and the simplest model. Well, what do you think about this model? Is it okay? Or maybe it is not that good?
Well,
Okay.
it may be significant that rates, dose rate and morality rate, not constant in real life.
Yeah, it's the first problem. The A is not constant in the real life because the birth rate and the mortality rate, they depend on some factors, on the environment, some factors connected with the environment, with the amount of food and so on. So, it doesn't work. Another problems. So first is A is not constant in the real life. Okay, another problems in this model.
Maybe we don't have endless space at Earth for endless amount of people.
Yeah, sure. That's the second main problem. If we consider the plot of n of t, we see that the population is growing exponentially to infinity. So it is absolutely not realistic situation because that's right, the space is limited, our planet is limited, and our resources are limited, and so on. That's the second problem of Malthus. So another problem of Malthus model, there is the absence of a self-regulation mechanism. What does it mean, a self-regulation? Let us consider a forest where do live some rabbits. Let's consider the most simple situation when there are no predators. So rabbits are eating the grass, and that's okay, no problem for rabbits. We understand that when the number of rabbits will increase, then they will start fighting for food. They will start starving because the food is limited. And then at some moment, their mortality rate will increase. So we need to take into account some mechanism of self-regulation. What was the first Malthus idea? He examined the existent situation for Europe of the end of 18th century, and he understood that the human population at that moment grew up exponentially, and he understood that food products production grew only with linear speed. And he said that, okay, we see that it is the food production, it is the population growing. And we expect some point when the food production will be less than needed to support the population. And then finally, we can see hunger. He introduced very simple solution. He said, okay, how can we decrease the fertility? Let us restrict to poor people to have a lot of children. It was a really bad idea, but it's the history. So it was his solution of the problem. The only positive of this model that the population biology appeared itself. It was quite understandable that the model is bad. So the next model was introduced very quickly. Another idea about some criticism of the Malthus model. At some moment, the sheep was introduced to Tasmania. There were no sheep on Tasmania before Europeans. And we can see the real life situation. A quick growing of the population of the sheep. And then the population stabilized near some point. So we want to have the mathematical model with a similar solution. There were no predators on Tasmania, but as the environment has some limited capacity, the sheep population stabilized near some point. In some years, the population decreased. In some years, the population increased, but still it was more or less stable. And the next one is the situation of whales. The population of whales, unfortunately, the hunt on whales led to exponential decrease of the whales population. Starting from 60s and 70s years, the hunt of whales was restricted, and we can see that the population more or less stabilized. I have no idea what is now, because it is well, 50 years old statistics. Maybe they decreased to zero. Maybe they stabilized with no impact of human hunting. So in the real life, both of the situation can exist. The population can vanish, and the population can stabilize. So we are going to elaborate some model with both of these situations. Next model is Benjamin Gompert's model. It was introduced quickly after Malthus, in 28 years after Malthus. And Gompert's model take into account the limitless of the environment. So he was examining the mortality or depending of the mortality of people or animals, depending on the age. And he understood that the probability to die at some age is the double exponent of a power with some constants. So he considered the differential equations with this solution, and he got the equation 3. A in this equation is our reproduction rate. It is the same as Malthus. Usually it is considered as the average number of children in the population. And L is some positive that describe the capacity of the population. So the question, what is L? What is L? What is the biological meaning of our L? Let us solve the equation first. How can we solve this equation? What should we do to solve it? Okay, I see we have to refresh our memories about differential equations. Okay, if we have an equation dn by dt is some function of n, we can multiply by dt and divide by f of n. We can write down the equation with separated variables, and we can integrate it. So we get some integral to the left-hand side and t plus c to the right-hand side. So in this case, dn divided by n, a n 1 minus logarithm L is integral of dt, like this. Dn divided by n is d logarithm n, and then we can easily calculate the integral. So the general solution after some simplification is a double exponent formula. Exponent of the exponent. You can calculate it by yourself. So finally, let us examine function 4. We are interested what's going on when time is going to infinity. Let's try to understand what will happen. We have exponent of negative at divided by logarithm L. L is greater than 1, so logarithm is positive, right? A is positive. So we have exponent to negative and growing power. So exponent itself, it goes to 0. It goes to 0, and all the function goes to L multiplied by n0 divided by L to the power of 0, and anything to any constant to the 0 power is 1. So for any positive a and L greater than 1, the solutions are going to L. Moreover, we can understand how do they approach L. If our initial value is greater than L, then the function is decreasing. And if n0 is less than L, we can derive that the solution is increasing. So the picture is like this. So if n0, it is the region when n0 is greater than L, and this is the region when n0 is less than L. So far, the population number is approaching L, and L is called the capacity of the environment. It's quite natural. If the population number exceeds the capacity of the environment, then it will stabilize, because the in this region n dot is negative. We can easily see if we draw a picture of the right hand side of the equation. We can draw a picture. Here will be n, and here will be n dot. If we draw a picture, we'll see that if the population exceed L, it is negative. The picture will be like this. If the population number is less than L, n dot is positive, and the population is growing. And if n is greater than L, then n dot is negative. And so it will start decreasing. It will start decreasing. We can easily see when we consider the quantity in braces. If we compare it with a 0, we can we quickly get an equation like logarithm n equals to logarithm L. Okay, the first task for you, let n0 be less than a half of L. Determine the time at which the largest population growth is observed. So what is the maximum of n dot? What is the time at which there is a maximum of n dot? We'll have some tasks. Some of them will be provided you at the examination, so you can prepare yourself. Next one. The Gompertz model was a bit complicated because there is a logarithm. It's hard to calculate. So Verhulst, a Belgian mathematician Verhulst, a few years later, introduced a bit more simple model with same features of the solution. Now, L must be positive, A is also positive. So the final solution, the general solution, is a bit more simple. And we can easily see that the same, when time is going to infinity, then n of t is going to L. And Verhulst predicted the upper limit of the population of Belgium as 9.4 million people. If you open Wikipedia, you can see that the current population of Belgium is 10.4 million. So the 200 years forecast is only 10% mistake. I think it is a very good good precision for me. Well, the model is very close to previous one, so I don't think I can add something. Maybe only the picture. Another task for you: use Matcat or Mathematica, or as you wish. Build on one plot the solutions of Verhulst and Gompertz equations and compare the solutions with the same initial conditions. And you can see the difference between Verhulst and Gompertz. Next one, a bit more general model. With the limiting environment. Let us consider a model 7. A is a positive constant, and f of n will be our limiting intensity depending on the population size. So we consider function f of n to be differentiable in the positive region. And what are another conditions for f of n? First of all, if the population number is 0, then the limiting intensity is equal to 0. It's quite natural. So the species do not fight for, if there are no species, that there is no fight between the species. Next, the function must be growing. The more species there are, the harder is the fight between them for resources. So f prime is positive. And next one, let's suppose that exists some population n with a tilde, such that f of n tilde is a. A question for you: what is the no positive n tilde? What does it mean from biological point of view? Is it okay from biological point of view or not? if there are no positive n, such that f of n tilde is a. No ideas. Well, let us consider the right-hand side of the equation 7. If f of n never reach a, so the quantity will remain positive. The quantity remain positive, and it means that the population number is always growing. So we decline this situation from biological point of view. We refuse it. So if we consider a limited population that have some really limited environment, then we can conclude that the point n tilde must exist. So the right-hand side must be negative from starting from some point. And usually we can see the equation with this feature when this f of n really exists. So if we consider this situation from the point of view of theory of stability of differential equations, we can conclude that we have two equilibriums in this equation, and the zero equilibrium is unstable, and the non-trivial equilibrium will be stable. And I think we have to refresh our memories about the stability. I think all of you had the lections and practices on the theory of stability of differential equations, right?
Yes, yes.
So something like 1 or 2 years ago.
Mm-hmm.
As we consider differential equations, we are always interested in stability or instability of our fixed points. So we have 15 minutes left, 15 or 20 minutes left. Okay, so let us refresh our memories about the stability. What does it mean? How do we analyze the stability of differential equations and so on? Well, can you explain me in simple words, what does it mean, the stability?
Something like if the graph remains in one range of values, I guess. So it's stable, maybe converges. I don't remember.
Well, I think it's close enough to actual situation. So, what is the stability? We have some solution. Let us consider some solution of our equation. We have n dot is f of t n. It's our differential equation. It is our time, and it is n. So what if we will change the initial value? This is our solution. solution that we are going to analyze. What if we change? What if we consider some closed solution? If the solution starts in some neighborhood, this is our neighborhood of the initial value. This is our n of t, n dot of t0. N dot. If all the solutions starting from this neighborhood will be close enough for all time, then we say that this the solution n is stable. If solutions starting from some neighborhood are going to infinity, or that are become far from our initial solution, then we say that the solution is unstable. What about the analysis? The simplest one, the simplest analysis is a linearization. First of all, let us refresh our memories about linear equation. If we have the linear equation of this form, and I'm sorry. First of all, if we have some fixed solution that we want to analyze, for example, n tilde of t, we can make a variable change. For example, y is n minus n tilde. Then we substitute our n with a y. So we substitute n with y in this equation. And we get another equation. Y dot is g of time and y. But the last equation will have trivial solution. So g of t0 will be equal to 0. So we can consider only the stability of a trivial solution, as we always can transform our equation with non-trivial solution to an equation with a trivial solution. Next one. If the equation is linear and we consider the trivial solution, when it is stable and when it is not stable. So it is like, it is like Malthus equation. Where is it? Here you are. Malthus equation, a linear one. When it is stable and when it is not stable.
When a is negative, it is stable, and otherwise is unstable.
And why?
So because if a is positive, then exponent tends to infinity.
Mm-hmm. And what if A is a matrix and n is a vector? How can we derive is the zero solution stable or not?
Something with eigenvalues.
Yeah, sure. That's right. So, so for a linear equation, we consider the eigenvalues of matrix A. And if all the real parts of eigenvalues of matrix A are negative, then the zero solution is stable. And if exists some eigenvalue with a positive real part, then the zero solution will become unstable. So if the right-hand side, let us consider the equation n dot is f. Let us consider autonomous equation only with f of n. First of all, how can we find our steady states or fixed points? What is the condition for equilibriums in this equation?
The right-hand side equals 0.
We consider the equation f of n tilde is 0. So all the solutions of this equation, all the solutions are our equilibriums. What does it mean, an equilibrium? Equilibrium means the solution is constant. The solution is constant, and we are usually interested what is happening in neighborhood. If the solution is stable, then all the integral curves are going to our equilibrium or remain close. For example, they oscillate near the equilibrium. So the most simple idea, we can calculate the linear approximation. So what is f of n? Let us calculate Taylor series expansion near the point n. It is f of n tilde plus the derivative at the point n is n tilde, n minus n tilde, plus something small depending on n minus n tilde. Like this. So we neglect with this small summand. This is 0 because n tilde is an equilibrium. And then changing variables from substituting n minus n tilde as, for example, y, we get the equation like y dot is a y. So, the eigenvalues of this matrix, give us the answer. Will the equilibrium n tilde be stable or not? And we remember that if there are some eigenvalues with a 0 real part, then we cannot say something about linearized equation, and we must use Lyapunov functions and so on. We'll touch Lyapunov functions a little, but we'll not try to calculate something or to prove some theorems. We just use the results. Well, some more about. I think I will finish today with the one model of the dynamic of one population. Next model, we can consider the situation when our growth factor, when our average kids number is not constant. So we upgrade Malthus model with this new proposition. The equation is still easy to analyze because we can solve it. We can get the exact solution. So an interesting question. If our environment provide us some, well, oscillating conditions, like, changing of time of the year, when in winter the conditions are bad and in summer the conditions are good, then our population growth depend on these conditions. So let us suppose that our function A is periodic with some period. And the main question is what will change with the result of Malthus equation? Will it still grow up or not? Let us introduce the average value on the period. So the average value of our increment. And we can form the, as we have the exact solution, we can consider the value n of time plus period. So if we consider this equation and substitute time with t plus big T, like this, it is exponent of integral. We can divide the integral into two. So this integral is integral from 0 to t plus integral from t to big T. And exponent of a sum, it is the product of exponents. And so far, n of t plus period is n of t exponent along the period. And from this expression, it follows that our population is periodic only if and only if the average value is 0. Another question for you. Let the average value is 0. Is the equality, the medium value of n is n0 valid? Oh, so if n tilde is an average population over the period, will these conditions satisfy? It's not that complicated. You can just calculate it. So you can calculate the average value along the period, and you'll see, will it be, will these oh, I forgot the word. So is it valid or not? Another simplification. Let us consider Verhulsten equation with periodic A. So in this equation, we can see that the exponent of AT becomes exponent of integral of A. And another question for you, let the average value along the period is positive. Prove that the limit of our population will be n. So it's a task for you. During the next lection, we'll consider a bit more complicated model with more complicated dependency between the population size and the factors that depend on fertility and mortality. And the equation will become more and more complicated. So I ask you to refresh your memories about the stability and the theory of differential equations in general. Well, I think that's all about our first lection. We have practice for groups number, just a moment, 2 of your groups. Groups. Where is it? Where is it? I don't see the timetable. What do you think? Should we make another group for practice, or we can stay here?
We can stay here if you want.
Generally, I don't think it makes a big difference.
Okay, so let's make a break. And and we'll continue for groups number 7 and number 8 in 10 minutes. Okay?
Okay.
Okay.